Good morning, everyone. Thanks a lot for the invitation to present at this conference. I'm really happy to be here. Before I get started, so I'm Helene, I work at Dartmouth College, but before I get started, I want to say that this is not my work. This is the work of a very large number of people who, please don't be offended if you participated and your name is not here. It's really trying to summarize a decade and a half of community efforts trying to improve projections of the Antarctic ice sheet. I want to say that this is the instant meeting, so I'm going to talk only about Antarctica, but very similar efforts have been done for Greenland. And because over the past 3 days, we've heard lots of things about processes that ice sheet models should include, all the data that are available and that these models should try to use, and all the motivation. And for this audience, I'm going to skip any kind of introduction of motivation and jump right into the results and some history. So we're starting here 1.5 decades ago, something like that. I was still a PhD student at the time. And this was the first effort where a number of people got together to try to do some projections of the Antarctic ice sheet with a number of ice flow models. And so you can see here you have about 6 ice flow models simulating the evolution of Antarctica. And that was a long time ago. We tried to, and we can see the evolution of sea level contribution from these models, and you have all kinds of results going from mass gain to some very significant mass loss over the 200-year period. This was from the Seroussi effort. And so these numbers were coming from projections based on A1B scenario, and this shows the change in surface temperature and surface precipitation that was applied for these experiments. There were a few experiments done, and we were just applying these surface anomalies, looking at the impact of climate, and then multiplying that by 1.5 and multiplying that by 2 to see like the range and sensitivity. And that was looking at the impact of climate and surface changes. There were also experiments looking at how the ocean and the basal melt under the ice shelves was impacting the results. And you can see here that for these runs, we added 2 meters or 20 meters or 200 meters per year of melt under the floating ice shelves. And very simplistic, very crude. That's the first time we worked together, and just we're trying to work on that. Another thing that these figures don't show is that some of these models did not have floating ice shelves. They did not have grounding line migration, and so in that case, they did ad hoc experiments trying to just put melt at the front of the glaciers because that's what they could do at the time. Okay, so what were the results of these Seroussi experiments? Well, for the first time, we had continental scale projections from an ensemble of models doing experiments and doing similar experiments to try to see how things would respond. So great things to just get started. Of course, there were lots of limitations because, as I just said, these models had sometimes no ice shelf representation, no grounding lines. The initialization was done in a varied number of ways and did not necessarily agree with the present-day state of the ice sheet. We also relied on climate models that were from the previous generation of CMIP at the time because of timescales and things like that. And some of the forcings were really highly idealized, such as this ocean forcing that I just talked about. But that sets the stone and the pace for moving forward and just a place to start. So what happened after that? Well, at the same time that there was Seroussi, there was also an European effort, IS2C. And so we decided to get together to just have like one effort to try to move our community forward. And that's how ISMIP6 was started. And ISMIP6 was endorsed as part of one of the MIPs in CMIP, so it was great to strengthen this link with the climate community and make sure we would be in phase and in tune with them. And the goal, so ISMIP6, and you've heard about that already this morning, so I don't need to explain. The goal was to estimate future sea level contribution from both the Greenland and the Antarctic ice sheets, and to look at the sources of uncertainty in these projections. So what did we do? The first thing was that, as I said, like models had lots of work to do to improve, capture important processes, improve their initial conditions. So we worked on, and developing these models take an awful lot of time. So we started right away to work on initMIP, which was an initialization experiment, so that models could get together and we could apply very simple forcings to better understand why we had all these results and where we were stating a few years later. And so the approach, and as in any of these results I will present, is come as you are. Modelers are doing that on their free time. These are like Sunday evenings kind of models that you do when you have time and you're not funded to do that. And so no constraints. We still had 2 constraints in that case because of what we've had seen before, that models had to have grounding line migration. How you do it doesn't really matter, but you need to be able to capture grounding line evolution. And also they need to have ice shelves because this is so critical in Antarctica. I don't need to explain that to you. And so what did we see with these results? So here we see the extent of the ice shelves in this model at the beginning of the round. And this shows how many models have for each pixel or grid points simulate an ice shelf. And you see here 25. That means that we had 25 simulations for this experiment, which is already like a huge increase compared to the 5 or 6 models we had before. We can also see that the position of the front position and the extent of the grounding line varies significantly between one model and the next. So that tells you something about like their initial conditions. And we can also look at the difference between modeled and observed thickness. The initial thickness of the models compared to observations. And some models capture that relatively well, some have more differences. This is the root mean square error. And then the same thing for the root mean square error in velocity, so how models reproduce or not these velocity that we are observing today. And so, but then some of these models that do that really well, then they tend to be initialized with present day conditions. So obviously they can capture that. But then what matters is not just the present day condition, but how you will evolve from that conditions. And so you see here under constant climate forcing how these models evolve and what's the trend and the mass loss over a 100-year period. And you see that some models have very small trend, some have quite some mass loss, but you also have a large number of models that have some mass gain with these constant climate conditions that represent the past 5 or 10 years. So all kinds of problems. And then we wanted to see, okay, well, what happens when you apply very simple anomalies first in surface mass balance, and there's a star here because this is the result subtracting the result from this experiment minus the control run that you have to see here to see what's the impact of the warming or what's the impact of this additional surface mass balance that you have. And you see that in that case, models agree pretty well. I mean, there's small differences, but we all agree how much mass gain we have in that case. Then we do the same thing with a very simple anomaly in ocean melt, and then the results are a lot more different. So depending how you apply your melt, someone just talked about that, about like what you do in partially floating areas if you have floating melt and things like that. That's what, depending also on the resolution of your model, that's why you have all these differences. So that was trying to understand a little bit how models respond to simple conditions and what we can learn from that. At the same time, we also had this big problem about being able to use better forcing from climate models. And so to work on that, we needed not just ice modelers, but also large participation from physical oceanographers, atmospheric scientists, people who look at climate models. And so we had long discussion and a really nice workshop in Sassenheim 5 years ago now. And you might recognize a number of people that are actually here in this room from this workshop. And we came up with a protocol to work to use results from global climate models and apply that as boundary conditions for the ice sheets. If I want to summarize that quickly, there were 3 things. The first thing was to select which climate models we would use, because there are several dozens of those, and we cannot run that many experiments. So we selected climate models based on their ability to capture present-day conditions close to Antarctica, as well as their how they would evolve over time. We didn't want to capture models that were just simulating lots of warming or limited warming. We wanted a range of climate models that had different behaviors. And so we selected 6 climate models, and unlike what we would have liked to do with the delay in these CMIP 6 projections, we still had to rely mostly on the previous round of climate models from CMIP 5. The next thing to do was to derive atmospheric forcing from these climates, and this is relatively straightforward. We did not use any downscaling or regional models. We just calculated surface mass balance from the different components of the climate models and apply that. The last part was the oceanic forcing. That was a lot more involved because many of these global climate models don't even simulate ocean circulation in ice shelf cavities, so we had to figure out what the conditions would be, and then find parametrizations that would do a decent job at simulating melt rate while being something that a lot of models could apply. So 3 things that went into that. And then we had our forcing for models. These are a list of experiments that were done, and here all the ice models that participated. And in a minute, I don't expect you to read all of that or remember any of this, but what the message here is that this represents what we have in our community in terms of like models used, resolution, parametrization, initialization, spin-up, and all of these things. So that's the only thing you want to remember here. What were the results? So if we want to summarize that in just like 1 or 2 slides, these graph shows the contribution to sea level rise, again, subtracting the control run with constant climate conditions for these 6 global climate models that we used. And we can see here that there's some evolution. Mostly, there is relatively little changes, about a few plus or minus few centimeters. We can see on the right here the spread for each of these climate models, so that these are all the ice sheet representation for each of these climate models. And so we see here that we have uncertainty coming both from how ice models respond to some forcing, as well as response to different forcing that comes from different climate models. And then if we want to dig a little bit deeper, we see that most of these things show limited changes, but it's not because nothing is happening. It's because you have competing processes and competing regions. And so if you break down this surface, into West Antarctica, East Antarctica, and the peninsula, we have first these diamonds that show the surface mass balance anomaly, so how much more surface mass balance you have compared to a control run for this region. And so limited increase in surface mass balance in West Antarctica, quite some increase in surface mass balance in East Antarctica. And then these diagrams show the contribution to sea level rise, and so the difference between these diamonds and the top of the bar is the dynamic contribution because of changes in ocean conditions, warming and melting under the ice shelf that affect the ice streams upstream. And so in East Antarctica, in East Antarctica, you have limited surface mass balance, so most models simulate mass loss. In East Antarctica, you have all this mass gain from additional surface mass balance, and then depending how much your model responds dynamically, how fast it responds, you can have either some mass gain or some mass loss, but mostly mass gain in East Antarctica. So that's what you have in these figures, competing East and West Antarctica, mass gain because of surface mass balance, mass loss because of dynamic response to these changes. Okay. So if we want to compare what we had in sea rise and what we came up with ISMIP6, well, we continue to have large participation from a really much larger number of models that were able to do continental scale simulations. We had improvements for some of the key processes such as ice shelves, grounding lines. Initialization is still something that is a problem, an active problem that we've heard about this week, so I don't need to explain more than that. Improved forcing from climate models, especially in the sense of like how to go from large climate models to forcing for the ice sheets, but also still some delay in terms of like mostly relying on CMIP5 models. There were some follow-up efforts using CMIP6, but that was still, this timing is always difficult, as we all know. So this was until 2100, and we said that we're overall maybe limited changes compared to some of the talks we've seen this morning. So we wanted to go beyond that and see what would happen beyond 2100. And so that's some effort that started 2 years ago, extending these experiments until 2300. And you can see the list of submissions done here. And you see, as time goes, this is getting smaller and smaller on purpose. I just left that this way so you can see like the increase in number of simulations and the extent of the results that we have. And so what we have here is still like about 16 modeling groups participating, but we have a lot more sets of simulations because people are interested in a number of processes and therefore submitted their own ensemble of projections looking at the impact of GIA, melt parameterization, resolution, and all these things. So we end up with this really long number of simulations that have lots of information in there. What do they say? Well, so that's what we had before. Until 2100, with limited changes, using these 4 climate models, mostly the same, 2R CMIP5, 2R CMIP6, so kind of similar to what we had in the previous ensemble. And then that's what happened if you extend that to 2300. And then the picture starts to change completely, maybe mid-2150 or something like that. And you can get up to more than 4 meters of sea level rise from these models. So, and again, you have the uncertainty coming from both from climate models and ice sheet models. So, and if you look at where these changes happen, we can look at these maps showing for 21, 22, and 2300, the thickness change between the beginning and the end of the run. And so we see that 2100, we had lots of melting for the ice shelves, but not much propagating upstream of that. A little bit located in Thwaites and Totten, but that's it. If we start looking at 2200, now ice shelves have melted significantly, and we start to see that this thinning is happening in Thwaites. Totten continues, but also Saipol Coast and ice streams feeding into the Rhône-Filchner ice shelf, significant thinning there. And that continues well until 2300, at which point, like large parts, if not all of West Antarctica is starting to thin significantly. We can look at also at how the grounding line changes for this time stamp, and so same 2100, not much is happening. 22, 23, you have a little bit of grounding line retreat in the Totten region, and so sorry, I forgot to explain. These colors show the percentage of the ensemble that ungrounds at a given time, and so blue is like just a few members unground. Red means that all the models agree that the grounding line is gone at that time. And so limited changes in East Antarctica, I mean, it's not nothing, but compared to the significant changes we have in West Antarctica. And if we zoom on these regions, we see that models agree pretty much that grounding lines are retreating in this Bunghenstock region, Saipol Coast. The extent might differ from the models for Saipol Coast. And then we have Thwaites and Pine Island, and that kind of reflects what we've seen today, that some of the models show very rapid and large retreats, and other ones have very limited changes. And so then you have a lot more uncertainty, and we don't really know what's happening in this region. So from this ensemble, same thing as what we've seen this morning. And then, because we're starting to look at these longer timescales, we go back to questions that we've seen over the past few days with GIA, bedrock evolution, and what Heiko talked about, how we can calculate, because all these numbers I've shown, this is, I call that sea level rise, but Heiko would call that volume above flotation. And this is actually what it is, volume above flotation. But now that we start to look at these 3 centuries, some models include GIA and changes in bedrock elevation. And what do we do with that? And so again, going back, and thanks Heiko, it was perfect introduction this morning, looking at these 2 methods, what do these corrections look like if we look at this time scale? So a large number of models don't have any change in bedrock elevation. So the 2 methods agree that there's about 3% change when you include the density correction from fresh and salty water, and they agree. But then you have up to 10% changes for the models that include changes in bedrock elevation for this method, and 20% for this one. So this is one of the next challenges we're going to have. On top of ocean and atmosphere, we need to figure out what to do with that, because you can have significantly different results depending what you do on your bedrock. And this conference is called INSTANT for instability and threshold, so I could not finish before talking about this ABUMIP, Antarctic buttressing model intercomparison project that also builds on these models that were done for ISMIP6. And in that case, we want to remove the ice shelves entirely, either through melting them from really large and rapid ocean melting, or from calving any ice that's floating calves. And here are the results when you remove all these ice shelves over a very short period, how things change depending if you apply melting or calving, and we can see that over this 500 period, we have really large changes up to 12 meters of sea level rise. And these are the simulations from all these models, and they show again that West Antarctica in some cases is collapsing completely. In some cases, some parts remain, but very large parts are removed during this period. Okay, so where are we now after all these experiments? And I mentioned a few things already. The first thing is that we can compare our results with the recent observations. And so we have IMBI results. Here, this is the blue line here, and I don't know why the 2 standard deviation is not showing, but it would be a very thin light blue shade just around that. So We don't see it, I don't know why, it wasn't my slide, I promise. Very thin line here. And then we have all these ISMIP6 results for the historical period, and then for some projection, ISMIP6 started in 2015 here. And you can see that maybe there's one model that agrees more or less with observations. I'm not sure why, that might just be a coincidence, but most of them don't agree at all. And so what do we do with that? This is still our problem of initialization, initial conditions, and capturing the recent trend that we still have a lot of work to do on that. Another thing is that I talked a little bit about uncertainty and what are the sources of uncertainty. And so here, going back to the ISMIP6 2100 projections, we can look at the source of uncertainty here using all the high emission climate scenarios. And so in that case, we saw in INTMIP that the response to first mass balance was the same for all the models. So I'm just looking at the impact of ocean forcing and dynamic response. And so we do multivariate analysis to look at how to partition the uncertainty in terms of ice models, climate models, and emulation. Why emulation? Because some experiments did not exist, so we just filled in the gap with some emulation for that, not to bias the ensemble too much. And we can see on the scale of Antarctica how things are changing in time. And so you have this climate here that's increasing slowly in time to reach 10–15% of the uncertainty by 2100. And then the biggest chunk is coming from the ice flow models. And then you have this ice-climate interaction, and here we have only ocean, so it's just ice-ocean interaction depending on the geometry of the ice shelf, the melt parametrization, and all these things related to ocean. And so that's for Antarctica. But then if you look at different regions, and so here we have Antarctica, and then we have, for picking up 4 of the glaciers that are contributing most to sea level rise, we have Thwaites here. And for Thwaites, climate plays a really small part, less than 5%, while both ice and ice-ocean interactions play a significant role. But if you look at Institute or Totten Glacier, the uncertainty is pretty much spread between these 3 sources almost equally. And then if you look at McHale ice stream, you have the climate, the source of the climate, so what climate models you use, that represents more than half of the uncertainty, because in these cold cavities, you have some climate models that start simulating warm conditions by the end of the century, and therefore you have completely different conditions, and you can either keep a cold cavity and stable ice stream, or warm cavity and completely destabilize it. So the uncertainty is not just ice model, it's a number of things, and it's complicated because it varies spatially as well. So what are the challenges that we're facing now? So I mentioned a number of things during this talk, and I just want to come back to a few points and questions that I think are important. First, we're starting to see that some groups and people submit ensembles of simulations because they're interested in some of these processes. But you don't want to bias these ensembles because one group is submitting 10 simulations while another one, who's maybe running at very high resolution or using a full SOX model, something like that, has only one. So how do we take this into account and take advantage of the full simulations that we have without biasing our estimates? I don't know. Another thing is that we start to see how emulators and these kind of techniques can be used to fill in the gaps and improve distributions, not having 10 or 20 simulations, but fill in and give us better distributions. So what do we do with these experiments we want to design? Do we design them around these emulators? But we also want to be able not to use emulator and just to look at the raw results. So how do we reconcile these different experimental setups that we have that we want to design? Another thing for which I don't really have answers. And then borrowing some really nice cartoons from Frank. Here, and that's something we've seen over these past few days, here are the number of processes that are discovered based on observations, data, and all these things. And this is increasing exponentially and really rapidly. And then here are the processes that we include in these models. I'm pretty sure I can name all of them. Rounding line, ice shelves, calving maybe now, and not every process is included in every model. So what do we do with that? What are the processes we need to include? We've heard a number of these processes recently, but which are the ones that we need to start with? Which are the ones that's the most important that we should focus on? Related question, and again, borrowing that from Frank, here are the number of people claiming that ice sheet models need improvement. And I've heard that many times over the past 3 days, and that's great. That means I have probably work for the next 50 years at least. Wonderful. Here are the number of people working on these models. So what do we do with that? And as I said, all of these models are done on Sunday evenings. That means that there are a little bit of core funding from Click and activities like that that help us get together, have workshop and talk and discuss. But there's no funding for running these models. And it's actually really hard to get NSF or NASA or any agency to be excited about, okay, well, I'm going to do the same experiment as 10 other people because we need together to learn about uncertainty and where we agree, where we disagree. So we have limited people, we have limited funding. How do we do that? Another challenge I would really love us to solve, but anyway. So yeah, I'm going to stop here. I just want to, with one point only, saying like how far we've come from these 5 models with completely drastically different results to an ensembles. We can really have agreement in some of the regions, some of the processes. Even though there's uncertainty, we can start capturing things more. And the uncertainty is no more just an ice problem. It's like also working with climate communities and other people, all of you in this room, to make things better. So I'm going to stop here and again thank all the people who participated in these efforts in their spare time. Thank you.
Amazing. Thank you for that, the run-through of all of that work that's been done over the last few years. We've got quite a bit of time for questions.
I'm just going to add too, Helene, thanks very much for that, because that's going to set up the panel discussion for this afternoon really well and into tomorrow. The challenges that you laid out there, I've heard reflected from many people in the room, and so trying to address them, help ISMIP and the ice sheet modelling community and our community as a whole address those challenges is a key goal for this group. So thanks for setting that up. Now I'll stop talking and see if there are questions.
So I'm a paleontologist, so not a modeler. I'm here.
Oh, sorry. Yeah,
no, that's fine. No, I really enjoy your talk. But as a specialist, what's your feeling about in your community? What are the best models that we could trust more? I mean, and I don't mean, because you say there is these Sunday models, and then you have a few labs who have the money and the time and many grad students to really refine the model. So, as a non-modeler, which one can I trust more?
That's a great question. I will say it depends, because if you're looking, and so lots of differences come into the way models are initialized, and some are initialized through paleo timescales, and therefore they capture better the trend or a relatively limited trend in the recent changes. But then they can start with conditions that are quite far from today's observations. And on the other hand, you have models that that are more focused on the past 2 decades or just the short time scale and initialize with data assimilation to reproduce present-day conditions perfectly. But then as soon as they start running, they have bigger trends and deviate more quickly. And so depending on the question you're after, one model that will be better than another one, and maybe some will capture some regions better, or so parameterizations that they use apply more in cold or warm ice shelf cavities. So I'm sorry, this is like what a Swiss answer or something. Like I'm not going to answer. And like as someone who's worked with all these models, I know that none of them is perfect and none of them is bad either. They just have different strength, and so I would definitely defer from saying that, but happy to, depending on the question, some might be more relevant than others, that's for sure.
Be careful, you're recorded.
That's okay, I didn't say anything too critical. I did good.
It's an incredibly diplomatic answer, I think.
It's recorded.
Come on, Helene, I would have started by saying that they were all wrong. But some are useful. Another thing, what about bias corrections in the climate forcing? Because the climate forcing gives a very, very large spread. Would it be possible to reduce that spread somehow in the forcing of the ice sheet models?
So when we derive, for example, if you go back to the melt parameterization, when you derive that, we knew what the melt was over the past 5 years or so. So we made sure that to provide parameterizations and parameters that would allow to reproduce these melt rate that we have observed. But then the climate models had, were sometimes have bias in these cavities, and actually they don't even simulate the cavity. So we first have to extrapolate conditions, which is not perfect, but what we have to do. And hopefully the next round will have more include these cavities. And so we have to, and they have biases, so we already have to correct for the average temperature based on the few observations that we have, because we also have few observations in around Antarctica and ice shelf cavities. What's the temperature salinities? And they're biased because we mostly go there when there's no sea ice. So what does it mean for like year-round conditions? So we had to calculate that and add some temperature corrections. And then we assume that they're constant over time, but this is obviously not true. So yeah, no, and that's why this is not just an ice model problem. We need the help and progress in all of these other disciplines, all the things we've heard about, and beyond that, so if we want to improve the projections. So yeah, we're happy to have all of you here in the room and can help and contribute in any way to these efforts.
I believe we have one more question, potentially. Yeah.
Thank you. I'll give you a choose your own adventure. Do you want an ice dynamics question or a climate question?
You can pick.
Let's do climate. So it's a very exciting takeaway that Thwaites doesn't really care. The uncertainty around Thwaites doesn't really care about climate, or it's low. Is that it doesn't care about climate, or is it that we know the climate better in the projections?
Great question. This is the percentage of the uncertainty coming from these things. And so in the case of Thwaites, first of all, it's already a warm cavity, so there's limited space for warming even more, unlike cold cavities. Also, the uncertainty from the different simulations that we have is relatively large. You've seen, like, when we continue to 2300, some models simulate like large deglaciation, and some models don't even show that much changes on Thwaites. So there's to start with, there's a much larger uncertainty, and then in that case, the trend and like how models can capture or not the recent changes has a significant impact on the results. So it's both because there's limited space for more warming, and because the ice models have such different trajectories that it represents a small fraction of the uncertainty in that case. Yes.
Awesome. That's about time for questions now, so thank you very much. Next up, we've got Helene, who's going to be talking about her long-term